Okay, so we continue with the examples of quantum operations and quantum noise. And today we are going to discuss uh, amplitude damping and phase damping. We are going to get to that. So first, look at the problem of energy dissipation from a quantum system. How do we describe it? So this can arise in a variety of physical phenomena. For example, examples of energy dissipation, and this might include spontaneous emission of a photon from an atom. It might also include scattering or attenuation of a photon from an interferometer, or for example, approach to equilibrium of a spin system in an environment. Now, as we discussed, the operator formalism, quantum operation formalism with operation elements, it can describe all sorts of physical conditions, physical interactions between system and the environment, and the general behavior of all these processes can be captured by quantum operations, and all these are called by an umbrella term of amplitude damping. So as an example, consider a photon going in an interferometer, and this is the state of the photon, and I model the environmental interaction with a beam splitter. This is my beam splitter. This thing scatters into the environment, this passes off, and this is a beam splitter with the interaction Hamiltonian given by the unitary matrix this guy. This is the unitary matrix of the mu splitter. So initially we are going to assume that the environment, just as an example, let's assume that the environment has the state 0. So one has 0, this is the initial state of the system and environment. It can be shown upon the application of U. In fact, do this and convince yourself. I get this guy plus cosine theta 10 times sine theta. So let me just write it as this guy. Now one may trace out the environment to see the effect on the system. And well, why don't we just explicitly do it? We try to trace out the environment. So I'm going to write now from the state of the system environment psi. Let me write down the density matrix rho, and that's going to be, of course, this guy A star this guy, and when I solve it, this becomes this guy. Writing it in terms of the density matrix, this becomes, so this is just a photon going through an interferometer interacting with the environment, which we have modeled as a beam splitter. These are my diagonal terms, and I'll have the off diagonal terms. As this guy. In terms of quantum operations, I can represent this as some process with the operation elements where I can express E0 and E1 where gamma is nothing but sine square theta can be interpreted related to the probability of losing the photon. So notice what happens. E1 is going to, what's the effect of E1 on let's say the zero ket? It's going to basically destroy the zero ket. Is going to give you whereas what is it going to do to the ket 1? It's going to reduce the amplitude. Is going to change, reduce the amplitude of the ket 1. Sorry, it's going to change 1 to 0 with a certain amplitude, and it's going to destroy 0. 0 becomes the null vector. What about E0? Now E0 is this guy, and this is going to leave 0 unchanged. Whereas what does it do to one? So I have it essentially reduces the amplitude of 1. Well, this happens because, of course, the quantum energy was lost to the environment. So this is what happens. And in general, this is an example of the amplitude damping process. We gave one concrete example of it when I had a photon going through an interferometer, and I could model the system as a photon interacting with the environment, and the operation elements were either changing 1 to 0 or they were reducing the amplitude of state 1. That was what was happening. So to picturize what is happening on the Bloch sphere, it's kind of nice to see what are the invariant states. What does the quantum operation do? What states of the system it will leave invariant on the Bloch sphere? So for example, we had the phase flip operator. Remember, we had in the last lecture, we had the phase flip operator. And what did it do? It took the set of all the states on the block sphere and it contracted it along the z direction. So it turned a sphere into an ellipsoid along the z direction. And just a reminder, this was the operation elements of the phase flip operator. So this was the phase flip operator. So what are similarly speaking, what do you think are the set of invariant states of the amplitude damping channel? So I'll just tell you, so that's the question. By the way, what were the set of invariant states? Remember, it's for the phase flip, it's contracting in this direction, and the z-axis is the set of invariant states. Nothing will happen to any state lying on the z-axis because it's a contraction along the z-axis. So similarly, what are the set of states invariant under the action of the phase flip, sorry, the amplitude damping channel? Remember, the operational elements in this case were, we just did it, this guy and this guy. And as we saw, this was causing, let me just see if I labeled them correctly over here. Yeah. And as we discussed, over here, E0 was causing the energy lost to the environment, and E1 was causing a change from 1 to 0. So if you look at it, which is the state? Nothing happens to that particular state. So it's just the 0 state, isn't it? So the invariant set of states is just the 0 state. Why do I say that? Well, the action, so let's say my density matrix was this guy, and what happens through my quantum operation, this is this guy, and this is going to do nothing. This is going to destroy the state, so the state remains still this thing, which was what I started with. So the state 0 is the set of invariant state for the system. So eventually that's the only invariant state of the system, but we can ask the following question: what sort of interaction with the environment will lead to invariant state 0. What sort of environment? Or, pause a while and think why 0 is the only invariant state of the system. And why is this happening? So remember, I'll give you a hint. We assume the environment itself to be in the state. And this is as if environment itself is, think about it, environment is in a pure state 0, 0, as if environment is occupying the lowest energy level. An artificial scenario, but that would happen when the environment is at 0 temperature. Usually the environments are a lot messier than that. So now our challenge is to slightly extend this above case of a 0 temperature environment, and we ask the following question: can we go a step up? Can we generalize the dissipation process to an environment at a finite temperature? And this is described by something known as generalized amplitude damping. Channel, I'll just name it as quantum operation generalized amplitude damping. So I have this guy. These are the quantum operation elements for the generalized amplitude damping, or in the scenario, these two. This guy. So notice that for p equals to 1, our generalized amplitude damping channel reduces to the usual. So p equals to 0, all I have is, p equals to 1, all I have is these two guys, reduces to your usual amplitude damping channel. Uh, so what are the set of stationary states for this? And this is given by, I'll just write it down as, and this is certainly a process. So this is my equilibrium state at t equals to infinity. Uh, and this is known as the T1 relaxation process. And the question is, what determines P? Remember, P was always 1 in the amplitude damping channel. Here we have two parameters. This was, let's say, the probability of a loss of photon to the environment, which we were modeling as a beam splitter. This was gamma. Remember, gamma was related to the probability of the loss of photon or something. P was a factor that determined the weight of these Krauss operators and or the operation elements. And what determines P? It's the temperature of the environment. That was something, remember, we generalized it. For a zero temperature environment, P was always 1. So temperature of the environment determines P, the value of P. That's also going to tell me how much proportion of P is there in state 1, like state 0, and what is the population of P in state 1. That's going to be dependent upon ultimately the temperature of the environment. So for example, at temperature T, the qubit state reaches, any guesses? They reach the equilibrium value. Which is basically where Z is this guy, and this is called as the Boltzmann distribution, where the population of every energy level is weighed by this particular factor. So this is the Boltzmann distribution. That is what determines the value of the equilibrium distribution. So now the next question we can ask is that what happens to the amplitude damping? What does the amplitude damping do to the Bloch sphere? So we have this gives us I can take gamma, for example, to be, let's assume that, so let us look what is it doing to the Bloch sphere. So as you can see, remember gamma was, what was it? It was related to the loss of a single photon in the beam splitter experiment. So one can assume that as time goes to infinity, I am eventually going to lose the photon. So that's going to go to 1. So let me just put gamma as a thermodynamic process of which basically means that gamma is temperature dependent, and as my time goes to infinity, I get gamma to be 1. So ultimately what's going to happen is on the Bloch sphere, due to the amplitude damping, I have the z, I have the x, I have the y. There is a shrinkage happening in all directions. And everything is shrinking towards the North Pole. And finally at t goes to infinity, I just get 1 point as the invariant state on the North Pole. So this is the amplitude damping channel. And ultimately the system reaches its ground state because of the environment. Shrinks towards the North Pole. What about the generalized amplitude damping? Well, it has two factors. It has got a P and a gamma. And the generalized amplitude damping, in general, it's going to also do a similar thing to the Bloch sphere, but the final invariant state is not going to be the ground state. It's going to be some other state on the, eventually it's going to contract to some state z 2p minus 1. That's going to be your final invariant state. Remember, that's because of the environment is at a finite temperature. So both the amplitude damping channel is contracting about the North Pole from all directions of the Bloch sphere, finally to the ground state on the North Pole. This is contracting about certain particular point, which is going to be here, depending upon the temperature of the environment. Remember, P was dependent upon the temperature of the environment. So that's the generalized amplitude damping channel and its action on the Bloch sphere. So amplitude damping was an example of energy dissipation, as you saw. It not only was shrinking the Bloch sphere in this direction, it was also shifting the Bloch sphere, contracting the Bloch sphere across the North Pole. So that ultimately, let's say the amplitude damping channel, ultimately I reached the ground state, or I lost all the energy of the system basically. Now, with which we modeled energy damping. Now the question might arise that can there be loss of quantum information without loss of energy. So I have a state to start with, and let's say I can write this as my density matrix form. These are my diagonal elements, and I get this is my initial state. One way for this to happen is I lose the off diagonal elements, and I'm only left with a square and b square. Also notice that the diagonal elements were, so this was, for example, the probability of occupation in energy level 0. Similarly, b square was probability of occupation in energy level 1. We can see that. So if I measure the system, I have this density matrix, I measure it with projector operators, and the trace of this thing gives me the probability of being in this guy, where of course my P0 was and P1 was so that gave me the probability a square, and this was b square, this was p1. So the bottom line is that regardless of what the off diagonal elements are, the probability of occupation in 0, the ground state or the upper level, first excited state, doesn't change. So the expected energy of the system remains the same. So this is a process of losing the off diagonal elements where I am not losing energy, but still I am losing some information. And this is known as the process of losing only the off diagonal elements is known as phase damping. And as you can expect, one can look what happens to the Bloch sphere geometrically. I'm having a contraction about the z-axis. So this is the phase damping, or losing my off diagonal elements, and this is causing a contraction along the z-axis. So which is what we saw exactly in the phase split channel. So which is same as we saw in the phase flip channel. So as far as the effect on a single qubit is concerned, phase damping or the loss of off diagonal elements is exactly equivalent to phase flip. You know, considering its effects on the Bloch sphere. So as an example, you remember the example of the energy dissipation or the amplitude damping was a photon in an interferometer which could have got lost to the environment. Over here, the example of the phase damping would be photon scattering without losing energy. Photon scattering, where it loses the phase information randomly as it travels through a waveguide. Or, so this is example number one, or phase damping would be atomic states in an atom get perturbed due to electric fields influenced by external electric fields, so on and so forth. So intuitively what's happening is that the state of the system undergoes a random kick which can be modeled by a rotation in the z direction on the Bloch sphere about z axis. So as part of your homework, maybe I can assign some problems where you're going to see actually how concretely certain environmental interactions with the system leads to this kind of a rotation on the Bloch sphere. Right now, just treat it as what's happening phenomenologically, what's its effect on the Bloch sphere about the z-axis. So this random kick is called as the phase kick. So what one does is that when one averages over many such kicks, let's say averaging over a Gaussian distribution of RZ theta. So the kicks are by the rotation angle theta in where theta is a random variable picked according to a Gaussian. So I'll get we average the density matrix by the rotation operator where each of these rotation operators is picked through a Gaussian distribution and integrate over whole theta to obtain a density matrix with the following elements. So this is the exponential decay. So alternatively, similar processes can be described by the following operators. So this was when I had averaged over an entire spectrum of random kicks by a Gaussian variable. Well, or I can treat it as a discrete process, which is some alpha, nothing happens to the Bloch sphere, and with the probability of 1 minus alpha, square root of 1 minus alpha, I have the phase flip channel. So the bottom line is that over here alpha is this guy. So the bottom line is that the process of phase damping can be either modeled as a continuous process where we integrate over a lot of random kicks, or modeled as a discrete phase flip process as we saw. And as far as the effect on the Bloch sphere is concerned, it's exactly the same. What does it do to the Bloch sphere? We already saw that. It's a phase flip channel. This guy is taking the Bloch sphere and contracting it, changing it into an ellipsoid, contracting it in the z direction. So this is called as the T2 relaxation, where one loses the information about the phase. So T2 relaxation process is just the exponential decay of the off diagonal elements in the density matrix. We already saw it doesn't cause any energy dissipation, whereas contrast this to T1. T1 was the decay of the diagonal elements, decay of the diagonal elements. So notice phase damping was analogous to the T2 process, whereas the amplitude damping consisted of both T1 and T2, because amplitude damping took my Bloch sphere and shrunk towards the North Pole. So amplitude damping was, or doesn't matter, the generalized amplitude damping took my amplitude damping involves both T1 and T2. Okay,